Transition element is an element that forms at least one stable ion with an incomplete or partially filled 3D subshell. Let's take a look at some examples. So for example, in the case of titanium, you'll be able to form Ti2+ after losing 2 electrons from the 4s. Therefore, you will have a partially filled 3D subshell. Hence, Ti2+ is transitional. So similarly, titanium can form Ti3+, and when it forms Ti3+, it will lose 2 electrons from the 4s subshell, and you will also lose 1 of the electrons in the 3D. You'll find that again, Ti3+ has a partially filled 3D subshell, which means Ti3+ is transitional. Let's now take a look at scandium. Scandium is deemed to be non-transitional since it can only form a cation with a charge of 3+, as it loses all its electrons in both the 4s and the 3D subshell. In this case, your scandium would have an empty 3D subshell, hence it does not meet the definitions of a transition element. As to the reason why scandium can only form Sc3+ and not 2+, is primarily because of its ionization energy. Let's now take a look at the ionization energy of aluminium and scandium. By looking at the pattern of the first to the fourth ionization energy, it is clear in the case of aluminium, the significant increase in the ionization energy occurs from the third to the fourth IE. Looking at scandium, scandium follows the exact same pattern as your aluminium, whereby the significant jump or the significant increase in ionization energy increases from the third to fourth. Meaning to say, the lone electron in the 3D subshell, which has very close energy level to the 4s, behave like valence electrons in the 4s subshell. Hence, because of this, scandium can only form Sc3+ by losing both electrons in the 4s and the lone electron in the 3D. The next 3D block metal, which is non-transitional, is zinc. The reason is because zinc forms the only cation Zn2+, and when it forms Zn2+, it will lose both its electrons from the 4s subshell. Therefore, zinc 2+ will have a completely filled 3D subshell, and hence because of this, it is non-transitional. To explain the physical properties of transition elements, we specifically look at 2 pointers. Point 1 is that as you move across the 3D block metals, additional electrons are added to the penultimate electron shell, which means the inner electron shell, and specifically in the case of 3D block metals, it is in the third electron shell, rather than the valence electron shell, where the principal quantum number is 4. So by adding electrons in the inner electron shell, it contributes to shielding effect. However, the 3D electrons have poor shielding effect, and that links to point number 2, because the difference in energy level between the 3D and 4s subshell is small, or we can argue to say that the 3D and the 4s subshell have comparable energy level. Based on both these pointers, we can now explain that the effective nuclear charge increases moderately. As every additional increase in the proton, there will be an additional electron in the 3D subshell that's providing shielding effect. However, the effective nuclear charge still increase moderately since the 3D electrons provide poor shielding effect. Therefore, because of this, the atomic radius and the first and second IE remains largely invariant, and the term largely invariant means more or less the same in terms of their values. And using point 2, given that the 3D and 4s subshell share similar energy level, electrons residing in the 3D subshell can now be delocalized, which means transition elements can delocalize more than 2 electrons, which explains why they form stronger metallic bond than generally group 1 or group 2 metals. Because the metallic bond is stronger, they occupy smaller molar volume, and with stronger metallic bond, their melting point would also expectedly to be higher, and being closely packed, it means their density will be higher, and transition metals will be harder. They will also be better able to conduct electricity since they have more delocalized electrons. And finally, they will also be able to display variable oxidation state beyond that of +2. Let's now show you the oxidation state of all the various 3D block metals. In the case of scandium and zinc, as earlier explained, they can only show the only oxidation state of +3 and +2 respectively. From titanium to manganese, the oxidation state they display will involve all the electrons from the 3D and the 4s subshell. So in the case of titanium, there will be 4 of them because electronic configuration of titanium is 3D2, 4s2. So the maximum oxidation state of titanium is 4+. In the case of manganese, the electronic configuration is 3d54s2. Therefore, because of this, it can display a maximum oxidation state of +7. Thereafter, from iron to copper, the oxidation state will start decreasing from +6 all the way down to +3. Hence, in conclusions, with the exception of scandium and zinc, all the rest of the 3D block elements can display variable oxidation states, which means they can display more than one oxidation states. And the maximum oxidation states of the 3D block elements is your manganese, which is +7.